Let's look at the math of heat transfer between two objects. Let's say we have an object here that's in contact with an object over here, or maybe we have an object that's in contact with another object, but there's some kind of insulating material between them, not perfectly insulating, or maybe the two objects are in touch with each other through a smaller part, so they can't transfer heat as quickly. And we're going to pretend that all around the objects is some kind of insulating material so they can't lose heat out the top or the sides or anything. So let's say one object starts at, let's say 4 degrees Celsius, like kind of right out of the fridge, and the other object is at maybe 25 degrees Celsius, kind of a warm room temperature. And now we have to say, what's the rate of change of object 1's temperature? And then what's the rate of change of object 2's temperature? So take a second and think about how the rate of change of temperature should depend on the current temperatures. All right, well, you might say the bigger the difference between the temperatures, the stronger the heat flow should be. If the two temperatures were the same, then we should have no heat flow or zero rate of change. So we could say the rate of change of object 1 should be proportional to the difference of the two temperatures. To say proportional to, let's come up with some sort of heat transfer coefficient. And I'm just going to use 0.3. It depends on how much insulation is between the two things. It depends on what the materials are made of. It depends on how big they are. There's not a lot of calculus in determining that, but there's a lot of other physical sciences. So I'm going to say multiply the heat transfer coefficient times the difference of these temperatures. And we have to wonder about which direction to take the difference. Temperature 1 is colder than temperature 2 right now, so temperature 1 should be warming up. So I want a positive answer for the rate of change of temperature 1, so I'm going to do the currently larger number minus the smaller number, and that will give me a positive number for the rate of change there. And then for temperature 2, I'm going to use the heat transfer coefficient times the difference of the temperatures, but again, temperature 2 is warmer than temperature 1, so temperature 2 should be cooling down, so I want to do the subtraction in a way that would give me a negative right now. So I'll do the other temperature minus this temperature. And then what rate of change, what should the new temperature 1 be? We'll use the calculus prediction formula and say new value equals previous value plus rate of change times delta t. So new value equals previous value times rate of change times, and I'll put a dt here in just a sec. And I'm going to do something sneaky. I'm going to put in a $sign before the column reference there. So when I drag this over, I'll keep referring to the delta t column, but the other column references will change, they'll move over one. Alright, so let's put in delta t, which is just the next time value minus the current time value. And so we see that the temperature of object 1 went up a little bit. And now, if we did our formulas right, we can just fill this over, and it looks at now temperature 2 and temperature 2 prime and still the original dt. And then we can fill these formulas down. And we see that since the two temperatures are closer to each other now than they were before, the rate of change is not quite as big because there isn't as much of a difference between them. So I can fill this down and fill these down. And then what's the next thing we should do? Maybe graph some stuff. So we'll come back to that in a sec. Alright, so let's graph this. We'll highlight time, Control-Shift down arrow, Control-Shift right arrow to highlight the big block of data, and then we'll insert a graph. Let's use connecting lines, straight lines with no markers, and let's see if this makes sense. We have object 1 temperature warming up and object 2 temperature cooling down, and they eventually reach the same temperature. The derivatives, the object 2 has a negative derivative at first because it's warming up. Object 1 has a positive derivative, but the derivatives go towards 0 and eventually there's no change in the system. The dt column we don't really need to see, so I'll just click on that data series and hit the delete key. And the last dt value looks strange, and that's using a cell that's blank, so that doesn't really make any sense, so we'll just delete that. I didn't really have any mathematical idea of how far out to go here, but running things until the temperature isn't changing anymore seems to make a fair bit of sense. So, let's see, we should label our axes here and everything, so we'll choose a layout that has axes. So this axis is time, and this axis, it's kind of temperature, or rate of change of temperature. I was thinking of degrees Celsius. All right. So here's a big question. What assumptions was I making in this model? What limitations did I have? So we mentioned that we're assuming object 1 and object 2 are not losing or gaining heat from the surroundings, that they're super insulated. So that was a big one. And the other one that is kind of implicit in the way I drew the pictures, and it's in the formula essentially, is that object 1 and object 2 are the same mass, and their mass heats up at the same rate if a particular amount of energy flows in. Object 1 and object 2 are the same mass, have the same heat capacity. If we wanted to have them to have different masses or different heat capacities, we can do that. It doesn't really change the calculus all that much, but you can put that in if you want. See, we assumed that the heat transfer coefficient didn't change with time. I don't know if heat transfer coefficients tend to change probably not with time. Maybe they change with the current temperature of the materials. So it doesn't change with time or with current temperatures. So those are some big assumptions that we had in making the model. The idea that the rate of change of temperature is proportional to the difference between the two objects, that's called Newton's law of heating or cooling. The rate of change of temperature, or actually you could say the heat flow rate is proportional to the difference in temperatures. So that's heat transfer between two objects, and then in other videos we'll do more complicated things.